been waiting all day. So the next lecture, so this lecture I would say is like decent. The next lecture is going to be a good one. And it'll happen today too, so that's cool. Yeah, twofer today. So let's talk about decibels for a second. Although it's not a type of signal, and we were just kind of going through a bunch of types of signals, I'm going to pause and mention decibels alongside sinusoids. The decibel, dB, is a conventional logarithmic ratio of amplitudes. That's filled in for some reason. Yeah, so write that down. So in any case, let A1 and A0 be amplitudes expressed in decibels. So we would write it like this. So let A1 and A0 be regular amplitudes. Say they're like voltage, like they're 5 volts sinusoids. So say you've got V1 equals A1 sine omega 1t, and V2 equals A2 sine. Typically, if you're going to be comparing amplitudes, you're going to have the same frequency. So let's just say omega 1 is assumed to be equal to omega 2 here. But A1 in general is not equal to A2. I want to compare these two amplitudes. So I used 1 and 0 in this, but in any case, you can take the ratio of these two amplitudes, and you can take the base 10 logarithm of that ratio, and you can multiply it by 20, and you will get yourself a dB ratio, decibel ratio. It's a conventional thing with a long history, but it's convenient when you have an exponential relationship between the amplitude ratios, and then you take its logarithm, and it ends up being linear when you graph it. So that's one reason to use decibels. Mainly we teach it to just propagate it as information that people once, really thought was important. I honestly don't find a lot of value in decibels, but people, you're going to see it all the time, so you got to know what it means. Is what it comes down to. It's like we didn't have to make college all about coming to lectures and watching professors talk, but we did it, and so now that's what we're stuck with. So we can't change it. So yeah, the reference amplitude, A0, sometimes called the reference amplitude, is sometimes taken to be 1, but typically it is some conventional quantity like 1 volt for a voltage signal. In certain cases, like this, the abbreviation dB might be given some decoration like dBV, which is to give you a sort of hint that, oh, we used for this decibel value 1 volt as our reference amplitude. So yeah, it shows up a lot, and then we're going to see that in system dynamic contexts, we even abuse this beyond all recognition. Notice that the amplitude ratio, they should have the same sign, right? Like they should both be in volts. So this would be a dimensionless ratio. Later we'll just compare amplitudes with completely different units, because why not? And once again, that's a conventional thing people decided to do, and we just keep doing it. So yeah, it's good times. The decibel is sometimes expressed in terms of the ratio of the powers of two signals, but we aren't there yet. Although if you're in mechatronics, you'll have seen that in the first chapter of the art of electronics. They do talk about power ratios. Essentially, it's the same, except for this is 10 log base 10, and then you do a ratio of powers instead of a ratio of amplitudes. Okay, so that was all I wanted to talk about decibels for now. Ramp and sawtooth function. So a ramp function is an aperiodic signal that increases linearly forever. So a ramp is just that, right? Forever. A sawtooth function is a periodic signal that repeats a section of a ramp function over and over and over again. So it kind of looks like a sawtooth. Okay. The triangle function is a periodic signal with a section of a ramp followed by a negative section of the same ramp. Below, a triangle signal with amplitude A and period T is plotted. So there's triangle. Notice how it's different than the sawtooth because sawtooth went up and then straight down, whereas the triangle goes up and then ramps back down. Ramps up, ramps down. I know. Pretty cool stuff. The square way, so these are all things that when you get in the lab, the function generators that are in there can produce all of these different functions. So you could put these all into a circuit and see what response happens. It's kind of cool. A square signal is a periodic signal that switches between two constant values. Below, a square signal with amplitude A and period T is plotted. So from like plus A to minus A, back and forth forever. That's a square signal. All right, that's all that I had for these. I just wanted to introduce those because we're going to start using them in this next lecture, which is really cool. Okay, any questions on signals, sines, square waves? Okay, sweet.